Dark matter is not as sticky as already suspected, Hubble Chandra found. By Mary Dupré on March 27, 2015. Dark matter does not decelerate when colliding with each other, which means that it interacts with itself even less than formerly predicted. Cosmologists using observations from NASA's Hubble Space Telescope and Chandra X-beam Observatory have discovered that dark matter does not ease off when colliding with one another. This implies that it interacts with itself even less than already thought. Scientists say this revelation narrows down the options for what this baffling substance might be. Dark matter is a transparent form of matter that makes up the most of the mass in the universe. Since dark matter does not reflect, absorb, or emanate light, it can just be traced indirectly, for example, by measuring how it twists space through gravitational lensing, where the light from distant sources is magnified and contorted by the gravitational effects of dark matter. The two space observatories were used to study how dark matters in clusters of galaxies acts when the clusters collide. Hubble was utilized to map the post-collision distribution of stars and dark matter, which was traced through its gravitational lensing effects on background light. Chandra was utilized to see the X-ray emanation from the colliding gas. John Grunsfeld of NASA's Science Mission Directorate in Washington, D.C. said, "Dark matter is a mystery we have long sought to unravel." With the mutual capabilities of these great observatories, both in extended missions, we are nearer and nearer to understanding this cosmic phenomenon. In order to learn more about dark matter, analysts can study it in a way similar to experiments on visible matter, by viewing what happens when it bumps into celestial objects. An exceptional research lab for this investigation can be found in collisions between galaxy clusters. Galaxy clusters are made of three principal ingredients: galaxies, clouds of gas, and dark matter. Amid collisions, the clouds of gas enclosing the galaxies collide with one another and decelerate or stop. The galaxies are significantly less affected by the drag from the gas, and because of the huge gaps between the stars within them, they don't have a slowing effect on one another. We know how gas and galaxies respond to these cosmic collisions and where they emerge from the wrecks. Comparing how dark matter acts can help us narrow down what it really is, said David Harvey, of the École Polytechnique Fédérale de Lausanne, EPFL, in Switzerland. Harvey and his colleagues used information from Hubble and Chandra to study 72 large cluster crashes. The crashes happened at different times, and are seen from different angles, some from the side and others head-on. The group found that, like the galaxies, the dark matter continued straight through the brutal crashes, without decelerating compared with the galaxies. Since galaxies pass through unrestricted, if cosmologists watch a partition between the distribution of the galaxies and the dark matter, then they know it has slowed down. If the dark matter does slow, it will drag and leave somewhere between the galaxies and the gas, which tells analysts how much it has interacted. The principal theory is that dark matter particles spread all over the galaxy clusters do not often bump into each other. The reason the dark matter doesn't decelerate is because not only does it not interact with visible particles, but it also infrequently interacts with other dark matter. The team has measured this self-interaction and found it occurs even less frequently than previously thought. Team member Richard Massey of Durham University, in the United Kingdom, said, "A past study had seen comparable behavior in the bullet cluster. But it's hard to understand what you're seeing if you have just one example. Each collision takes hundreds of millions of years, so in a human lifetime we only get to see one freeze frame from a single camera angle. Now that we have studied so many more collisions, we can start to piece together the full movie and better understand what is going on." By finding that dark matter interacts with itself even less than formerly believed, the team has effectively narrowed down the properties of dark matter. Particle physics theorists now have a smaller set of unknowns to work with when building their models. It is uncertain how much we anticipate dark matter to interact with itself because dark matter is already going against everything we know, said Harvey. We have concluded from past observations that it must interact with itself logically weakly. However, this study has now placed it below that of two protons interacting with each other, which is one theory for dark matter. Harvey said that the results propose that dark matter is unlikely to be only a kind of dark proton. If dark matter spread like protons do with one another, electrostatically, it would have been detected. This challenges the idea that there exists dark photons, the dark matter equivalent of photons, he said. Dark matter could potentially have rich and complex properties, and there are still several other types of interactions to study. These latest results rule out interactions that create a strong frictional force, causing dark matter to slow down during collisions. Other possible interactions could make dark matter particles bounce off each other like billiard balls, causing dark matter particles to be ejected from the clouds by collisions, or for dark matter blobs to change shape. The team will be studying these next. To further increase the number of collisions that can be studied, the team is also looking to study collisions involving individual galaxies, which are much more common. There are still some possible candidates for dark matter, so the game is not over, but we are getting nearer to an answer, said Harvey. These astronomically large particle colliders are finally letting us peep the dark world all around us, but just idealistic.